Welcome to part 2 of the high-power H-bridge inverter design series. In the previous video, we focused on the schematic and the functional building blocks of the inverter. Now we move to one of the most critical and often underestimated stages of power electronics design, the PCB layout. At high voltages and multi-kilowatt power levels, circuit performance is not determined by the schematic alone. Parasitic inductance, current loops, grounding strategy, and physical spacing begin to dominate behavior. Even a perfectly designed circuit can become unstable, noisy, or unreliable simply due to poor layout decisions. In this video, we will examine the practical PCB design techniques required for a 400-volt DC, high-power H-bridge inverter. We will discuss how current loops affect switching stress and electromagnetic interference, why creepage and clearance distances are essential for safety and reliability, how proper gate drive routing prevents ringing and false triggering, why grounding strategy directly influences noise and stability, and how PCB routing and wire design impact current carrying capability. We will then analyze the actual inverter PCB layout, looking at both the top and bottom layers, to understand how these design principles are implemented in real hardware. If you are designing motor drives, inverters, or any high-power switching system, this layout knowledge is just as important as the circuit design itself. So let us begin by exploring the PCB design aspects of a high-power H-bridge inverter. PCB design is a critical step in high-power inverter development. Even a perfectly designed schematic can fail if layout practices are poor. The following design aspects are especially important for reliable operation at 400 volts DC, multi-kilowatt power levels, and fast switching frequencies. Current loops. In power electronics, current always flows in closed loops, not in single traces. High di/dt loops exist in the DC bus, the IGBT, and the return path. They also exist in half-bridge switching paths. These loops must be made as small and as tight as possible. Large loop areas increase electromagnetic interference or EMI, voltage overshoot, and stress on IGBTs and capacitors. Design guidelines. Place DC bus decoupling capacitors very close to each half-bridge. Use wide copper posts or planes instead of thin tracks. Route forward and return paths close together to cancel magnetic fields. Creepage and clearance. At high voltages, electrical safety and insulation spacing are extremely important. Clearance is the shortest distance through air between conductors. Creepage is the shortest distance along the PCB surface. For a 400-volt DC bus, clearance should typically be around 4 to 6 mm. Creepage should be around 6 to 8 mm, depending on standards and environment. Design guidelines. Maintain generous spacing between high voltage and low voltage sections. Separate power circuits from control circuits. Use PCB slots or cutouts where additional creepage is required. Keep copper away from mounting holes connected to heat sinks. Gate drive routing. Gate drive signals are high speed and noise sensitive. Poor routing can cause ringing, false turn-on, and shoot-through. Design guidelines. Keep gate drive loops short and symmetrical. Route the gate and emitter return together as a pair. Place gate resistors close to the IGBT gate pin. Avoid routing gate signals near switching nodes or DC bus traces. Grounding strategy. Improper grounding is a common cause of unstable inverter behavior. Control ground and power ground must be clearly defined. High current ground paths should never flow through logic ground. Design guidelines. Use separate ground regions for the power stage and control electronics. Connect grounds at a single, well-defined point if required. Keep gate driver reference grounds local to the IGBT emitter. Noise control and EMI reduction. Fast switching edges create high dV/dt and di/dt, which generate EMI. Design guidelines. Minimize high-frequency current loop areas. Use proper decoupling at gate drivers, isolated supplies, and logic regulators. Add snubbers or filtering components if necessary. Keep noisy nodes away from PWM inputs, feedback signals, and debug headers. Summary. Good PCB design ensures reliable switching, lower electromagnetic interference, improved efficiency, longer device life, and safer operation. In high-power inverter systems, layout is just as important as the schematic. Careful attention to current loops, spacing, routing, grounding, and noise control is essential for successful hardware implementation. Let us now look at the PCB layout, showing both the top and bottom views of the inverter board. Starting with the top layer, this side primarily carries the power stage and high current components. The 4 IGBT footprints are placed in a straight line along the edge of the board, allowing them to be directly mounted onto a common heat sink. This placement minimizes thermal resistance and simplifies mechanical assembly. The DC bus input connectors, labeled HV+ and HV-, are positioned close to the corresponding half bridges. This helps keep the high-current DC bus paths short and wide, reducing parasitic inductance and voltage overshoot during switching. The output terminals, VO1 and VO2, are taken from the midpoints of the two half bridges and are centrally located to maintain symmetry between the left and right legs of the H-bridge. You can also see that the DC bus decoupling capacitors are placed very close to each half bridge. This is intentional and critical. It minimizes the high-frequency current loop area and significantly reduces switching noise. The gate resistors, protection components, and LED indicators are clustered close to each IGBT gate. This ensures clean gate drive signals and allows quick visual verification of switching states during testing. Now let us move to the bottom layer of the PCB. The bottom layer is mainly used for gate driver ICs, isolated power supply circuitry, and control routing. By placing these circuits on the opposite side of the board, we achieve physical separation between noisy power parts and sensitive control electronics. The isolated gate driver ICs are placed close to the IGBTs they control, keeping the gate drive loop length short. You can see that the gate and emitter return paths are routed together, which improves noise immunity and reduces ringing. The isolated power supply sections and their local decoupling capacitors are also tightly grouped around each driver IC. This ensures stable gate drive voltages even during fast switching transitions. A large ground copper area is used on the top and bottom layer to provide a low impedance reference for the control and gate driver circuits. This ground region is carefully kept separate from the high current power return paths. Overall, this PCB layout reflects the key design goals discussed earlier. Short and compact current loops. Clear separation of power and control sections. Proper creepage and clearance for a 400-volt DC bus. Clean, low-inductance gate drive routing. Good thermal and mechanical integration. With this PCB layout in place, the design is ready for fabrication, assembly, and hardware testing, which we will cover in the upcoming parts of this video series. In this design, signal connections use standard vias with a 50 mm pad and a 28 mm drill. This is adequate for logic and control signals, where the current levels are low and routing density is the main concern. For power paths, however, a completely different approach is used. In our design, large power vias with a 3 mm pad and a 2 mm drill are provided. These large vias significantly reduce via resistance and allow much higher current to flow safely between layers. In addition to the larger via size, the current carrying capacity of the PCB tracks is further increased by soldering copper conductors directly onto the power tracks and vias. This effectively increases the cross-sectional area of the conductor, reducing both resistance and temperature rise. By combining large diameter power vias with reinforced copper tracks, the board can handle high currents without overstressing the copper or the vias. This method is especially important near power devices, connectors, bulk capacitors, and ground return paths where current density is highest. So, while standard vias are used for signals, power paths in this design are intentionally strengthened using large vias and additional copper, ensuring electrical reliability and thermal robustness. PCB routing strategy and current capacity enhancement. All low-level signal tracks on the PCB are routed with widths of 10 mil or 20 mil. These widths are more than sufficient for the very small currents involved in control and logic signals, while also providing good mechanical robustness and manufacturability. Using 10 mil and 20 mil tracks improves fabrication reliability, reduces the risk of trace damage during soldering, and maintains good noise immunity for sensitive control signals. High current routing philosophy. For high current paths, the PCB layout follows a different design approach. Wider copper tracks, reinforced current paths, and thermal considerations are intentionally incorporated to support inverter-level power handling. H-bridge midpoint track design. The H-bridge midpoint track, which carries the inverter output current, is designed with an approximately 7 mm wide copper trace on the PCB. This wide trace helps reduce resistance and limit temperature rise during high-load operation. In addition to the PCB copper width, a copper strip reinforcement facility is provided. Dedicated pads are placed along the midpoint route so that a copper strip or heavy copper wire can be soldered directly on top of the track, increasing the effective conductor cross-section. This provides additional margin for high current testing and continuous 3.3 kW operation, while keeping the PCB design flexible for prototyping and future upgrades. DC bus routing and current capacity enhancement. The HV plus and HV minus connections between the two half bridges are routed on the top layer of the PCB. The base track width in this section is 2 mm, which by itself would be limiting for high current operation. To overcome this limitation, a current enhancement provision is intentionally included. Dedicated solder pads are placed along the DC bus tracks, allowing additional copper wire or copper strip to be soldered directly on top of the PCB. Overlay markings on the bottom layer indicate the locations where this reinforcement can be added. By increasing the effective copper cross-section, DC bus resistance and temperature rise are significantly reduced, making the layout suitable for multi-kilowatt operation. This approach provides flexibility during prototyping and testing, allowing the current capacity to be increased without redesigning the PCB. IPC-based current capacity estimation. For a printed circuit board trace that is 7 mm wide, with 35 micrometer copper thickness, corresponding to 1 ounce copper, the estimated current carrying capacity can be evaluated using the IPC-2221 standard. When the trace is placed on an external layer, such as the top or bottom layer, and exposed to free air, the allowable current depends on the permitted temperature rise. For a 10 degrees Celsius temperature rise, the trace can carry approximately 9.8 amperes. For a 20 degrees Celsius temperature rise, the current increases to about 13.3 amperes. For a 40 degrees Celsius temperature rise, the current capacity reaches around 18 amperes. If the same trace is placed on an internal or buried layer, heat dissipation reduces. In this case, for a 20 degrees Celsius temperature rise, the current capacity drops to approximately 6.6 amperes, which is roughly half of the external layer value. Practical current enhancement techniques. On all high current paths, the solder mask has been intentionally left open. This allows additional solder to be applied directly on the copper tracks, increasing the effective copper thickness. You can see that slots are milled into the PCB between the IGBT pins. By milling a slot in this region, the tracking path is forced into the air gap. As a result, the effective creepage distance becomes closer to the clearance distance, which is much easier to meet for high-voltage designs. This approach also helps prevent surface contamination effects. Flux residues, dust, moisture films, or conductive deposits cannot easily bridge an air gap, unlike a PCB surface. Over long-term operation, this significantly reduces the risk of carbon tracking and surface arcing failures, which are common causes of inverter field failures. This design practice is especially important in motor drives, inverters, EV chargers, solar inverters, and welding power supplies, where high voltage, fast switching, and harsh environments are expected over the product lifetime. In this design, the IGBTs are placed on the bottom side of the PCB, while their leads are soldered on the top side. Before soldering, the IGBT legs are bent by 90 degrees. This allows the PCB to sit flat against the heat sink, with the IGBT package directly mounted on the heat sink surface. Once the PCB is positioned, all the IGBTs can be bolted to the same heat sink, using a thermal pad for electrical isolation and good heat transfer. This arrangement provides excellent thermal coupling, keeps all power devices on a common heat sink, and ensures mechanical stability of the assembly. At the same time, soldering the leads on the top side allows for strong electrical joints and easy inspection after assembly. From this PCB layout, the electrical isolation is clearly visible between the high-voltage power stage and the low-voltage control and gate drive circuitry. The high-current, high-voltage regions are routed with wide copper posts and are physically separated from the control side by clear spacing, isolation gaps, and dedicated routing channels. You can also observe that no signal tracks cross the isolation boundary, and the routing ensures that creepage and clearance distances are maintained throughout the layout. This physical separation, combined with isolated gate drivers and isolated power supplies, ensures safe operation of the inverter, protects the low-voltage electronics, and improves noise immunity in a high dV/dt switching environment. Overall, the layout reflects a clear isolation philosophy, which is essential for reliability and safety in high-voltage inverter and motor drive applications. The PCB includes 4 mounting holes, each with a 4 mm diameter, positioned near the corners of the board. During assembly, 10 mm plastic spacers are used along with 3 mm bolts to mount the PCB securely to the chassis or base plate. Using plastic spacers provides mechanical support while maintaining electrical insulation, ensuring safe clearance between the PCB and the mounting surface. This mounting arrangement improves mechanical stability, reduces vibration, and helps maintain the required creepage and clearance distances in the high-voltage sections of the inverter. On this board, bulk DC-link decoupling capacitors are not placed directly on the PCB. Instead, the design assumes the use of an external electrolytic capacitor bank connected across the HV+ and HV- terminals. This approach allows the bulk capacitance to be sized according to the application requirements, such as power level, load type, and ripple current rating, without increasing PCB size or cost. The onboard capacitors are mainly high-frequency decoupling capacitors, placed close to the half bridges to handle fast switching currents, while the external electrolytic capacitors provide the required energy storage and low-frequency ripple filtering. This separation of bulk and high-frequency decoupling is a common and effective practice in high-power inverter designs. EE16 winding calculation using AI assistance. EE16 transformer winding calculation can be performed easily using AI assistance. To obtain meaningful results, the design requirements must be clearly specified. The following input parameters can be provided to the AI model. Primary voltage, ±12 volts. Maximum flux density, Bmax, restricted to 100 mT. No air gap. Split bobbin construction. Input waveform, square wave. Switching frequency, 80 kHz. Duty cycle, 38%. A series capacitor is included to prevent any DC bias in the core. Required secondary voltages, +15 and -9 volts, which corresponds to approximately 25 volts peak to peak. With these constraints defined, the AI system can estimate the required number of primary turns, the required number of secondary turns, and suitable wire gauge selections. This approach greatly simplifies preliminary magnetic design and accelerates transformer development. A split bobbin construction is used for the E16 transformer in the isolated power supply. This provides very high primary to secondary creepage and clearance, which is especially important in a 400-volt inverter environment. By physically separating the primary and secondary windings, the split bobbin reduces capacitive coupling, improves common mode noise immunity, and enhances safety isolation. Although split bobbins slightly increase leakage inductance, this trade-off is acceptable and even beneficial for low-power gate drive supplies, where isolation, noise reduction, and reliability are far more critical than tight coupling. This brings us to the end of part 2 of the high-power H-bridge inverter design series. In this video, we examine the key PCB layout principles, practical routing strategies, and the design choices used in the inverter board. In the next part, we will move forward to fabrication, assembly, and hardware testing. Thank you for watching, and I will see you in the next video.